powers, I'm like, can't we like restart from like after my associates? But they have to like press the issue every time.
Okay, we're going to get started, and I know I'm 30 seconds early here, but I know there were some questions about usefulness of this, and why are we, what's the point? So I'm going to read something out of the book here in reference to this thing called a Bessel function. We will see that the main use of power series is that it provides a way of representing some of the most important functions that arise in mathematics, physics, and chemistry. In particular, the sum of the power series in the next example is called the Bessel function, after German astronomer Friedrich Bessel. And the function given in the example we're going to do is another example of a Bessel function. In fact, these functions first arose when Bessel solved Kepler's equation for describing planetary motion. Since that time, these functions have been applied in many different physical situations, including temperature distribution in a circular plate and the shape of a vibrating drum head. So this is kind of an animation of a drum, right? And then if you were to hit it, what those vibrations would look like. Now, of course, this is exaggerated so you can see it, but that's the way that surface of that drum would work. And the function that models this is a Bessel function. So it's a power series. Now, I mean, that's a very, very, you got to trust that the Bessel function is related to this, but just again, trying to answer the question, what's the usefulness of this? I hope that helps a little bit.
So we talked yesterday about
They're already playing.
For alternating series, being able to take the derivative and
to see if it's decreasing? Yeah.
Should it work for every problem? That if it's convergent with the alternating series, it would be a negative slope?
No, it wouldn't have to be.
So the alternating series could say it converges, and you could take the derivative, and it wouldn't correlate?
Oh, no. Okay, I see what you're saying. No, it is a necessary condition.
It is a necessary condition.
That it's a decreasing.
Okay.
Yes.
I don't know if we went over that in class and I just missed it, but.
Okay. You mean the two conditions?
Well, I mean, because on the sheet it says the limit as n approaches infinity must equal 0, and that b sub n must be greater than b sub n plus 1.
Yes.
Is that a way of saying that the derivative is a negative slope that I don't know?
Okay, I see what you're saying. No, I never stated it explicitly that if we're trying to show a sequence decreases, if you can take the sequence and turn it into a function of x, then you can do the derivative and show that the slope of the tangent line is always negative, right? But what if your sequence can't be converted to a function of x? Like what if it involves factorials, or what if it involves negative 1 to the n or something? Oh no, it wouldn't, because we already took that out. But it could have factorials, so you couldn't do a derivative. So ultimately, you want to show it's decreasing by using the b sub n greater than b sub n plus 1. But if you can turn it into a function of x, just you can do the derivative. Does that make sense?
Yeah.
Can't use it all the time, but it's there. Okay, so I felt last class really didn't, I don't know, it just didn't sit well with me the way things were going. So I wanted to take a little time just real quick to review. What we were trying to do last class was define this thing called a power series about A. Okay, this is a power series. We say this is a power series about A, or sometimes you'll hear people say this is a power series centered at A. All right, and this was the formula that we looked at yesterday. Okay, or the other day. And now, if we define this to be a function of x, right? If we define it to be a function of x, then our ultimate goal is to figure out what x values will make that series converge. In other words, we're trying to find the domain of this function. And to do that, we'll use the ratio test to determine what x values make it work. And then we also must test the endpoints. And that was kind of where we were at the end of class last time. Yes? That's the basic idea? Okay, so let's do an example. And I'm going to do the Bessel function.
Could
yes.
you do a power series with factorial? With something with a factorial?
Yes.
You could?
Yes.
So can't you not turn it into a function of x?
You cannot.
Don't you have to do that here?
No, because we're using the ratio test.
Okay.
Yep. So this right here is an example I don't like that cursor blinking there. See it. Okay, so this is an example right now of what's called a zero order Bessel function. There's zero order, first order, second order, and don't worry too much about, like, again, where this comes from. I tried to start class by explaining that this can be used in all sorts of applications, but here's the function. And once I write it down, you'll recognize, hopefully, that this is a power series. It looks very complicated. That is a Bessel function of order 0. All right, so we do indeed have a power series here. You can see that we have, like, x to the 2n is really like x squared to the n, right? Something like that. So we have powers of x, don't we? Powers of x in this series. And then all this other stuff in here is like our c sub n, all right? So what we want to know, or what I want to do here, is find the domain of this. So to find the domain means I want to figure out for what values of x that this thing converges. So how do we do that? How do we determine when this series converges? Okay, should I go back to the note I just had up here? We want to know what values of x for which it'll converge. We will use the ratio test to determine those x values, okay? So we are going to use our ratio test to try and figure out when this series converges. So this is our a sub n, the whole thing. And remember, the ratio test says that we need to do the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, right? That's the ratio test. So I need to plug n plus 1 in for all this. Limit, you know, yeah, limit n goes to infinity. It's going to be a big, big mess. All right, this part, negative 1 to the n plus 1. Yeah, it's going to turn into a 1. Who cares, right? Now here, be careful. This is x raised to the 2 times n plus 1, right?
Wait.
I'm replacing all my n's with n plus 1s.
So just recognize that the plus 1 only applies to n.
Only the n, right? But the 2 would have to distribute.
Yes.
And then we have 2 to the 2 times n plus 1 again. That's this one. And then this, be careful, this is going to be n plus 1 factorial, because I'm replacing that n with n plus 1, but then all of that squared, right? That's a sub n plus 1. Now I'm supposed to divide that by a sub n, right? So because it's a fraction, I'm not going to put the fraction underneath this. I'm going to flip it and put it over here. So this is going to be 2 to the 2n, n factorial in parentheses squared, over negative 1 to the n x to the 2n. All right, now remember, I would like to see when this limit is less than 1, right? Because that would give me convergence. That's what the ratio test, right, is giving us. When we do this ratio test, what we want is this to be less than 1, right? Okay. Now, if it's greater than 1, it diverges. If it's equal to 1, it's inconclusive, right? All right, so we've got a lot of simplification to do here. All right, so I think I'm going to erase this. All right, limit n goes to infinity. And the whole idea here is that we want things to start to cancel. So let's get rid of the negative 1 to the n's first, right? These are gone. And this is that really good red marker that doesn't erase very well. Okay, those are gone. And then, let's see, this right here. See this right here? This is the same as 2n plus 2, right? If I distribute the 2 through. And so is this one. This is also 2n plus 2. Now, so if I want to rewrite this and split it up, I can rewrite it as what? X to the 2n times x squared, right? Isn't that how I could rewrite that? And then down here, let me see, this could be written as 2 to the 2n times, yes, times 4. I'm just going to go 2 squared though, okay, just because, yeah. Okay, so that's that. Now, n plus 1 factorial squared. This, I'm going to want that to cancel with that somehow, right? Something. So remember, we have something squared here, right? N plus 1 factorial is the same as n plus 1 times n factorial, right? That was that property we used where we peeled off that first piece. And now if I square it, I can square each one. Okay? So this becomes n plus 1 squared n factorial squared. Does that make sense? Sure? We're good? Okay, I think that's it for cleaning that up. Now let's just put everything else over here. This is just 2 to the 2n, n factorial squared, and then x to the 2n. And we're going to want this to be less than 1. So lots of stuff goes away here. 2 to the 2n, n factorial squared, x to the 2n. All of that's gone, isn't it? Anything else go? I think that's it, right? Okay, so now, at this point, let's see what we have left. Limit n goes to infinity. Okay, what's left on top? Just x squared. And on the bottom, what's left? So 2 squared and then that n plus 1 squared. Let's go ahead and square the 2 now. The reason I left it as 2 to the 2 in case it canceled. So watch how I write this. 1 over 4 times n plus 1 squared, right? And then times x squared. So yeah, I'm splitting it. I'm separating my n's from my x's. And the reason why is because the limit is only having an impact on the n, right? It has nothing to do with the x. So now, when we take this limit, what would we get? So you have to remember, we're fixing an x, right? If we fix an x, and in my other class, I don't know if we talked about the other day, but one of my students asked me, can x be infinity? And the answer is no, because x has to be a real number, okay? It's a number you're plugging into a function. You cannot plug infinity into a function. You can take a limit and say what happens as x goes to infinity, but infinity is not a real number, okay? So if this is fixed, then what does that limit go to? 0, right? So this whole thing goes to 0, no matter what. Agreed? So that's going to be equal to 0, because that goes to 0, and this is fixed right there. 0 times a fixed number, 0 times a fixed number goes 0, and you know what? That's always less than 1, right? And what does this mean? It means it doesn't matter what we choose for x, right? Any x we choose, this ratio is going to stay less than 1, no matter what x we ever pick, which means this thing will converge for all x's that we pick. Does that make sense? Any x we pick. So the domain of this, when I wrote that capital J of x, did I write that? Did I put a little subscript 0 underneath it? I don't think I did, yeah. I forgot to put this. That's what tells you it's order 0, sorry. So the domain of this function is everything, right? All real numbers, negative infinity to infinity. Everything. Yes?
Is it like a good habit to get into to split up your x's and n's?
Yes. Yep.
So
Okay.
If we get 0, it's...
Yes, if you take this limit and this goes to 0, your x's are always fixed, then this limit's going to go to 0, and that's less than 1, and you're good. The problems arise when this goes to something like 1 or 5 or something like that, or it goes to a nice number. Then x matters, right? Like, what if this limit went to 1? Then we would need x squared to stay less than 1, wouldn't we? Because this right here is going to be 1. This right here is going to dictate the actual magnitude of this thing. We're going to do some examples of that. Or if this goes to infinity, right? If this went to infinity, then the only way you can control this is to make that 0. So
Divergence?
it would diverge, yeah. Because the ratio test, we want this to be less than 1 to converge. And convergence here, convergence of this series means the x values that are within its domain. So the x values that make it converge is equivalent to the domain of this function. Yes?
Going back to our original sum, n started at 0.
Yes.
Does that change anything if it starts at another number?
Good question. No. And the reason why is, the question is, the original sum started at 0. Okay? And the question is, if we change that to like 2 or 5 or something else, does it change the answers in terms of convergence? The answer is no, because let's say we start the sum at 5 instead. That means we've missed plugging 0, 1, 2, 3, and 4 in there, right? So the difference between this sum and this sum is 5 terms, right? 5 numbers that are not being added. So if this thing converges, adding 5 numbers to it is still going to converge. Or if this thing diverges, adding 5 numbers to it is still going to diverge. So a finite number of terms added or subtracted from a sum does not have an impact on its convergence or divergence. Yes?
Is that kind of like when we have like the harmonic series and then we just add a constant to on the bottom?
Yeah, like with the harmonic, if we do something, add something on the bottom, it changes where it starts, but it's still harmonic. Okay.
Sorry, one more thing.
Yes.
So if the factorial on the bottom had been like n minus 1 and the index at the bottom had been 0, wouldn't it have been the index had been 1, the first term would have been out of the domain?
Yes. Well, even this one right here, the original one was n factorial, right? When you plug 0 in, you have to remember 0 factorial is 1.
Okay.
So, but if you had a series where you plug in a number and get division by 0, then something's wrong with the series. Like, it should start somewhere else. You have to, every one of your terms in your series has to be defined. You can't have division by 0 in any of them. All right, so this Bessel function. If we were to graph this Bessel function, right? Because it's a function, right? It has a domain. If we plug in x's, we get values, right? So if I actually plug in a value in here for x, this series will converge, right, to a number. I can't tell you right now what it converges to, but I know that if I plug 2 into the Bessel function, it's going to give me an output, right? Whatever it is. And I can do that for every number, any number. That means that the graph of the Bessel function exists on the entire number line. So it's a nice continuous function. Well, continuous, it may not be continuous, but it might jump, but there is a value for every single input, there's a value out. Okay? All right, let's do another one. How's it going over here? They tied. Yes. This is, oh shit. They're playing today 4 games that are timed at 25 minutes, which is a lot less time than they normally have. They normally have 100 minutes, and then once they get to 40 moves, they get an extra 30 minutes. So time's usually not an issue. Time is absolutely an issue right now. So 18 minutes, 19 minutes, that's all the time they have. I think when they make a move, they get 30 seconds.
Is this the first one?
This is the first game, yep. So, all right, next example. Oh no, not example, next note. Okay. This is a theorem, super, super important theorem, all right? I don't expect that you're going to write this all down. You can go back and look at this after class. So you have this theorem that says, look, let's say we're given a power series, right? We've got this power series. When you have a power series, there are only three possibilities. Three possibilities when it comes to the domain of this thing. First, it will converge at x equals a only. That's saying that for this series, look, if we plug a in, if we replace x with a, then this is going to be 0, isn't it? And then we have 0 plus 0 the whole way. And won't that converge? Yes, because we're adding up a bunch of nothing. So this always happens, okay? But the theorem says it's either going to be just that number, just x equals a, or it's going to converge for all x, which is everything. Like, 'cause that's the example we just did, right? We got all real numbers. Or it converges on some interval. Now, last class we did a problem where it converged on an interval. Yes? Right? We did that. I think it was the last example we did. Those are the only three possibilities. It converges at a single point, it converges everywhere, or it converges on a single interval. Now, when we talk about this interval, what we mean is that there's some number, capital R, such that when the absolute value of x minus a, which is this piece right here, when that is less than R, it will converge. Now, I'm going to have to do an example for you to see this, all right? But when we have this case, this third case where it's on an interval, that capital R is something very important. We call it the radius of convergence. And then I showed you last class how to deal with absolute values. I think I showed you that, right? The way you deal with an absolute value is, if I wanted to get rid of the absolute value, I'd drop the absolute value there, wouldn't I? And then over here, I'd put greater than, and what would go over there? Negative R. And then now solve for x. So get x by itself here. So add a here, here, and here. And when you do that, when you add a, wouldn't you get this right here? Okay, so x is bounded between, these are just numbers. So this is some number and some number. So x is between two numbers. This right here is called the interval of convergence. So we have two new ideas here. The idea of the radius of convergence and the idea of the interval of convergence. And when we do that interval of convergence, we could have there are four types of intervals in mathematics. There's where both endpoints are included. Remember, brackets mean include the endpoints. We could have both endpoints included. We could have the left endpoint not included, the right endpoint included, or the other way around, or don't include both endpoints. Those are our four possible intervals that we could get. And we're going to have to test our endpoints. All right, so this is the theorem. Let me do a couple of examples to kind of bring this all to light, hopefully.
So we can make every power series converge?
Every power series converges at least one point, x equals a. The question is that the only point? The only other possibilities are that it converges everywhere or on an interval. Okay? Yes?
Is it like basically a range of information we have from the function that it gives us? Like if it's only x equals a, like we only have 0, like we can't really say that much about it?
I'm not sure I understand your question. Can we do an example, and maybe in the example we'll resolve any of your open questions? Okay. All right. Find radius of convergence. We'll say that that's part A. Part B, find interval of convergence. So we're asked to find two things here. Well, I've got to start out with the ratio test. because the ratio test is going to tell me what's happening to this series, right? And it's going to be one of three outcomes. We're either going to get all real numbers, we're going to get a single point, or an interval. So let's see here. Limit n goes to infinity. All right, let's start plugging things in here. All right, n plus 1 goes in there first, right? So -5 to the n plus 1, and then we have x to the n plus 1 over n plus 2. That's n plus 1 plus 1. Okay. And then I'm supposed to divide that by a sub n, but I'm going to multiply by the reciprocal. So what goes here? Root of n plus 1 on top. -5 to the n here. And then x to the n here. Now some cleaning up. Limit n goes to infinity. Okay, we have -5 to the n times -5, x to the n times x over root n plus 2 times root n plus 1 over -5 to the n x to the n. So you see how I split these up, right? Those got split up like that. Here, 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 here. So now let's take a look at what we have left. All right. In terms of n's, I have this root and this root, right? These two roots have n. And I also have this -5. But I'm going to take the absolute value of that, right? So it's going to be +5. With me?
Right.
So I'm going to write it this way. 5 root n plus 1 over root n plus 2 times x. So I've split up the x from the n's, right? I actually don't need it anymore, but what if these roots came out to be negative? They're not going to, but there's no harm in, we need to keep it because we don't know what x is, okay? X could be negative, and we need to take the absolute value of it still.
It's like
right?
a precaution.
It's not a precaution because we don't know what x is.
Well, that's what I mean. I'm like, well, we don't know what X is, so we'll keep it.
We have to keep it, exactly. But we know that the -5 is irrelevant because it will become a 5 when we take the absolute value. Okay, now, what happens if I let n go to infinity?
Infinity over infinity?
Yeah.
Get infinity over infinity, right? So why don't we do this? Since these are both roots, why don't we do this? Can we do that? We're allowed to do that, right? If we have root on top, root on bottom, we can make it one big root. All right, it looks like the 5th root, right? Yeah, sorry, no, that 5 is supposed to be out here. 5 times that. Okay, so what happens here? Yeah, you can go inside, then infinity over infinity, L'Hopital rule, you'll get like 1 over 1, and that's going to be 1, so you get 5. So at the end of all of this, after you take the limit, we get the absolute value of 5x, don't we? We've done the limit, and that goes to the absolute value of 5x. And what do we need that to do? Be less than 1. Bam. Okay, now, let's remember what it's looking for. What we're looking for here. Radius of convergence means that we're trying to make it look like this. The absolute value of x minus a needs to be less than some number r, and that's our radius of convergence. So in our problem, our original problem, you see where we had x to the n? That's really like x minus 0 to the n. Do you all agree with that? That's x minus 0 to the n? So really a in the problem is 0. So I need to basically figure out if I can make this look like, make that over there look like the absolute value of x is less than some number r. Right now I have the absolute value of 5x. So I'm just going to use some properties of absolute value that you can do the absolute value of each one. Absolute value of 5 is 5, absolute value of x is absolute value of x. And now I can divide both sides by 5. So I have the absolute value of x is less than 1/5. Yes?
So you, whatever number you get over there, like whatever you get for a, you gotta make sure that it's,
You got to get that, whatever x minus a looks like over here,
you gotta make that one.
you got to make that less than some number. Okay? And then that number right there becomes your r. So what's capital R for us? 1/5. So we can answer this first part. Capital R is 1/5. That's our radius of convergence. Now I will actually explain why they call it a radius of convergence after we finish the problem. Now what we need to do is find the interval of convergence. Right? That's part B. To find the interval of convergence, what we're going to do is take this expression right here, and we're going to drop the absolute value. So when we drop the absolute value, we get x is less than that and greater than negative 1/5, right? That's me just dropping the absolute value and introducing the left side. And do we have x by itself here? Yes. So this is our interval of convergence so far. So far. All right? We're not done. Because if you look back, what did I say we have to do when you're looking for your interval of convergence? Yeah, interval endpoints must be tested. Okay, so right now we know for sure, that this series will converge so long as your x's are between here and here. What I don't know is what happens here and here exactly. So now I have to test that, all right? So here I go to test it. So this is not the answer. This is not the answer to part B yet. So now I'm going to test the endpoints. So let's test x equals, what if x equals negative 1/5? So what I'm trying to figure out here is whether or not I can do that or not. And whether or not I can do that or not. Do I include them or not? So, do y'all understand why this is? I think you do, but we were back here. Remember when we were back at this expression, we were saying we need that to be less than 1? Well, if x was negative 1/5, then wouldn't this become negative 1? And the absolute value of that would be 1, right? And then this wouldn't be less than 1, it would be equal to 1. And the ratio test is inconclusive. Inconclusive. So we actually have to go conclude whether or not it's convergent or divergent. All right? We know what happens when it's bigger than 1, right? Diverges. We don't know what happens when it's equal to 1. That's why we have to test the endpoints. So, test it. When we test it, well, that means you take x and you get to plug it in back into the original problem. Okay, here we go. Sum n equals 0 to infinity, negative 5 raised to the n, and then x is right here, right? So negative 1/5 raised to the n over root n plus 1. And now we're asking ourselves whether or not that converges or diverges. So what can we do here? We can put those together, right? Because they're both to the same power. So we can put them together and we can put negative 5 times negative 1/5, which would be 1. Exactly 1, right? So that'd be 1 to the n. I don't need the n, all right? Right, that's what I would have, which is really sum n equals 0 to infinity of 1 over root n plus 1. Okay. Does that converge or diverge? Ooh, something just happened. Oh yeah, this converges to 0. That doesn't tell you anything. Remember, and term test, right? So now we are back in 8.2, 8.3, and 8.4 right now. Because we have an actual series, right, without x's in it. How are you going to tell me if that converges or diverges? You could compare it to a p-series, maybe, right?
Yeah, right, starting to -1/2.
You mean change this to a 1? You don't have to. Okay? So in the very beginning I said let's start at 1, right? We're always going to start at 1. And that is now, we can always shift that index back, move it either way. We can start -5 if we wanted to. This is really kind of a dummy number. Is that all right with you? When we start with 1, it's just because it's easier to explain the idea of when you have a sequence, you plug in 1, output, 2, output, 3, output. But really, we could have started by plugging in -5, output, -4, output, and it just keeps going up by 1 each time. All right, well, I mean,
Compare to 1 over.
you want to compare? Okay, so I'm not going to say this is right or wrong. I'm just going to go with it, all right? So do you understand? Maybe you'll understand this part. The beginning of this problem, we have to do ratio test, right? To figure out all this stuff, radius of convergence. Now we're trying to find the interval of convergence. And to do that, it looks like we're going to have to test 2 endpoints, which means we're going to have to do 2 series individually and determine convergence and divergence on each one of them. So there's a lot in this problem, isn't there? So this is equivalent to giving you 2 problems out of Chapter 8, Sections 2 through 4. Could be any problem from out of there. All right, so you want to compare it to what?
1 over n to the 1/2.
Okay, so the idea here, I'm just going to erase all this, is we're going to do comparison test. And the a sub n that we're looking at is this. And you want to compare it to what?
So 1 over n to the 1/2,
Okay, 1 over root n, which is n to the 1/2, which is a p-series, right?
which diverges.
P-series, p being a half, which diverges. Everyone with us here?
A sub n must be greater than b sub
So we need to show that this has to be bigger than that. A sub n must be greater than or equal to b sub n. And I believe you're about to run into some problems. Right? What's wrong with that idea? Think about it. This denominator is bigger than that one, right? If this denominator is bigger than this one, then this fraction is smaller than that one, and that inequality is not true. So does that mean, what does this mean?
Test failed.
The test failed. So we need a different test. Now I actually like this comparison. I like what you're comparing it to. What I don't think worked was this type of comparison test. What other type of comparison test could we potentially use? Limit comparison test.
A sub n over b sub n.
So instead of doing this, let's do the limit comparison. Yeah. So if we change this to limit comparison instead, then we still use a sub n and b sub n, right? But we don't do this anymore. What we do is the limit as n goes to infinity of a sub n over b sub n. And what are we hoping to get here? A number that is, you can look at your sheets. It's fixed, positive, right? Has to be a positive fixed number. Okay? So let's do this. If we take the limit as n goes to infinity of a sub n, which is 1 over root n plus 1 over b sub n, which is 1 over root n. And then we do limit n goes to infinity. Let's flip them. Root n over root n plus 1, which is the same as the limit as n goes to infinity of root of n over n plus 1. What does that go to? Take the limit inside, do L'Hopital. You get 1 root 1. This is 1, right? Which is bigger than 0 and is a fixed number, right? So what does the limit comparison test tell you? If your limit turns out to be some constant bigger than 0, whatever one of them does, they both do, right? Whatever one of them does, they both do. And we know this one diverges. So that means that this one diverged, which means that this diverged, right? Which means we don't want to include negative 1/5 into our interval. We don't want to include it. All right? So this is divergent. Yeah, okay, right here. Therefore, when x equals negative 1/5, the series I'm just rewriting the original series. That was the original series, right, that I started. The whole problem started with this. That right there, when x is negative 1/5, diverges. All right, now what do we have to do? Check the other endpoint. Okay, let x be 1/5 this time. Then the series becomes negative 5 to the n, and then 1/5 to the n, and then over root n plus 1. So what's the difference going to be here? Now it's a negative 1 to the n on top, right? So it's alternating. It's an alternating series. And are you happy about that or not? Yeah, you should be happy about that because the alternating series test is much easier to implement than the one we just did, right? With the alternating series test, we really only have one test. Just out of curiosity, what would the ratio test give you here? What do you think the ratio test would give you here? 1. Okay? That's where this whole thing came from, right? The whole idea was that we knew it was between here and here. We didn't know what was happening here and here because the ratio test would have given us 1. So if you plug 1/5 in and then go, oh, I'm going to get clever and be ratio test, you're just going to waste your time because you're going to get 1. So we have to do some other test here. All right. Well, alternating series test. Here we go. Alternating series test. All right, we have to show two things, right? First, well, what is b sub n for us? Can you tell me what b sub n is? It's the part that doesn't have the alternating in it, right? That part. So it's the part without the negative 1 to the n in it. So it's 1 over root n plus 1. So I need to show two things. First, let's do it this way. I'm doing backwards. The limit as n goes to infinity of this must go to 0, right? And it does. So that part was easy. The next thing I have to show is that this is a decreasing sequence. So I need to show that b sub n is greater than b sub n plus 1, eventually. Right? So I need to show that 1 over root n plus 1 is greater than 1 over root n plus what? 2? And you can cross multiply this if you want. And you could even square both sides now. But it's obvious, I think, right? That's bigger than that. Okay, so we're good. So what does it do? It converges, right? It converges, which means we can include x equals 1/5. Therefore, if x is equal to 1/5, the original series converges. So finally, we have our answer to part B. The interval of convergence is negative 1/5 less than x less than or equal to 1/5. Or, if you like, you can write it this way.
So what's the difference between The other time it was therefore when. Does that make a
Oh, did I say when, or you mean for negative 1/5? I said when?
Yeah.
Yeah, you could say when.
Okay.
Yeah, therefore when this is true, then that converges. I'm just trying to summarize like what we have concluded here. Okay, now let's just see if we can't see the distinction between the radius of convergence and interval convergence. Would you agree first that finding the radius of convergence was easier than the interval of convergence? Because you don't have to test endpoints to find capital R, all right? All right, so what does it mean? Okay, let me draw a number line. Let's say, where was this series right here? We said that this looked like x minus 0 to the n, right? So we would say this is a power series centered at 0, right? That's what this would be. So if I go to 0, here we go, and then that's where I'm centered at, then look at my interval. I go to the right 1/5 and to the left 1/5. I don't include that point. I include everything in between, and I do include this point, right? So there's my interval of convergence shown to you, right? The radius of convergence is actually the distance from the center of convergence out this way. That distance is 1/5, right? And then if you go the other direction, right, this distance is 1/5. So think of it like a radius of a circle. You go out in every direction a certain amount. Well, here you go on the number line to the left of your center and to the right of your center by the same amount. Now, in this problem, because our center is 0, it's just the same thing each way. But what if our center was at 1? Then this would be 1 and then 1/5 this way and 1/5 that way. So this would be like 1, this would have been 6/5, and then this over here would have been 4/5. Does that make sense? Okay. So if we were to graph this as a function, that original series, if we were to graph it as a function, the picture would only exist between here and here. We'd have picture, and then outside of that, that function doesn't exist. Okay. What's going on here? What? The chess game's getting good? Oh, he's running out of time. That's strange that he's running out of time. I was telling the class that earlier that I already told you, this guy's the champion, this guy's the challenger. He's ranked number 1 in the world at classical chess, at rapid chess, and at blitz chess. All 3 he's the best in the world at. This guy's ranked number 2 in the world at classical chess. He's ranked 8th in the world at this format and 16th in the world at the next format, which is where I think they give him like 5 minutes each or something. Anyway, all right.
That guy's like the chess master.
He has been for a long time. All right, so that was a pretty involved problem, yes? Yeah, he might. He might run out of time. He's going to lose?
Why you guys aces?
I don't know. This is still a lot of time. 4 minutes is still a lot of time for these guys. Especially in that position, there's not a whole lot of pieces on the board. Oh, he's probably trying to do a pawn march here and get a queen. All right. All right, let's see. We are done with 8-5. Believe it or not, I hate to say it, but that's the only example that I'm doing in 8-5, which means you need to do your homework. You can imagine how long it took me to do the videos for that homework. It's a lot of work. Okay, but if you work through it, you'll see a lot of the little intricate details. Okay? All right, we are moving on to 8-6. So I know one of the goals in the class here, at least one of you has a goal that you want to be able to integrate something that we can't integrate without series. And this section is going to get us into this. This section deals with, okay, let's say we have a function that we already know, like a function that we've already dealt with in our life. Is there a way to take that function and turn it into a power series? All right? So how do we convert or represent a function as a power series? So remember, recall this. Recall this particular power series. Sum n equals 0 to infinity of x to the n. That was the first example that I gave you of a power series, right? That was the first one I gave you where I said that that thing in front was 1. You have to look back in your notes. But this is 1 plus x squared plus x cubed plus x to the 4th plus dot, dot, dot. Okay. Now, when does that converge? This is for me. Y'all aren't allowed to look at this anymore. When does that converge? No? I mean, it's in your notes. At least you can look in your notes if you don't know.
0?
For what values of x does that converge?
Oh, less than 1?
When what's less than 1?
X.
Not just x, the absolute value of x.
Geometric, right?
Yep, this is geometric. That is in your notes, right? Yeah. Last class. It would have been last class. Okay? So this will converge. This is important that you understand this. This is a geometric series. This is a power series, but it actually is a geometric series. This is when we said, let's let c sub n be equal to 1. So all the constants in front are 1s. Okay, so this converges if the absolute value of x is less than 1. Exactly, that's it. All right? What does it converge to? So if this is less than 1, then what does that series converge to? Good. So remember, geometric converges to a over 1 minus r. Remember that for geometric? Here for us, a is 1, right? All the numbers in front are 1, 1, 1. So it goes to 1 over 1 minus r for us is x. All right. Now, what I want you to see now is that let's say somebody gave you this function f of x equals 1 over 1 minus x. So what if I gave you this function? I said, hey, everyone, look at this function right here. You see it? Can you rewrite that as a power series? Yes, it's this power series, right? So long as the absolute value of x is less than 1. Right? So there is a way to go from this expression back to this, so long as the x lives within some certain interval. Let me do an example. Yep.
Is it because, like you're going the other way around, like they give you the function and you're going like the other way?
Yep.
I guess? You said it, well, it's, it's less than 1. But is that because if you plug in like 1, you get 1 over 0?
Yes. Yeah, that's why the absolute value has to be less than 1. So what I'm saying is this. If you were to take this expression, 1 over 1 minus a half, okay? Then x here is 1/2, right? This is the same as 1 plus a half squared plus a half cubed plus forever. Okay, that's what I'm saying. But that works for any x I plug in, so long as the absolute value of it is less than 1. Okay, let's see if you can do this one. Express this as a power series. What's that?
So would it be like 3x to the n?
I think so, yeah. So when we just did that power series a second ago, I want to rewrite it over here as a reference, just to have it. But I want to do something different. Instead of using x to the n, I want to put u to the n. And this will be 1 over 1 minus u, so long as the absolute value of u is less than 1. So that's exactly what we just did a second ago, but instead of x's, I'm using u's, all right? So if we look at this, do you all agree that we could call this our u right there, right? So according to this formula, that expression is equivalent to the sum n equals 0 to infinity of 3x in parentheses to the n, right? The whole thing to the n.
Does it have to start at 0?
Yes. Now, this is only true when?
When 3x is less than 1.
You can say when or if the absolute value of 3x is less than 1. That's the only time that this would hold. Does that make sense?
So it's no longer just the x because the 3 is there.
It's everything that was there. It's almost like a u, like a substitution. So this is like our u. So this becomes this. Now, this is a power series, right? But it's not written in the form that we're used to seeing it. So watch what I do here. Now, why did I do that? I want it to look like c sub n x minus a to the n. See, I wanted it to look like that.
So that would technically be the x minus 0.
This is x minus 0 to the n, and that's your c sub n. Understand? So there's my power series. I've expressed that. I've taken that expression, and I've expressed it as a power series. All right? Let's do another one.
So the end result, you would use the 3 to the next to the n? Or is that just showing?
Wait, say again?
You have to split it up like that at the end? Or?
You don't have to, but I would. Yes, I would. Because they want it to look like a power series. That means they want you to be able to identify the pieces. And we're about to start differentiating things and integrating things. So you want to separate them. Yeah. Okay, so let's go 3 over 1 plus 5x. Let's do this one. Express this as a power series. Oh my gosh, look at the time left. We have a couple of issues here. We have a 3 on top, don't we? Okay, also, that doesn't look like 1 minus u on the bottom. It looks like 1 plus something. So how about I do this? I start out by just pulling the 3 out because it's a constant, and I can just pull it out like 3 times something, right? And then 1, now check this out. How about minus negative 5x? Isn't that the same thing?
Yes.
Right? That's just a clever way of rewriting plus 5x. And now, does this look like 1 over 1 minus u? Yes. So this should be 3 times the sum, n equals 0 to infinity, of whatever it is that's here, right? Which is negative 5x, the whole thing, to the n. Now this is equal to sum, n equals 0 to infinity, of 3 times negative 5 to the n times x to the n. So again, I split this up into 2 so I could isolate the x. And the 3 that was out here can just come in and just be 3 times that. Now don't turn that into a negative 15, right? You can't do that. All right, now when is this true? I mean, this right here is equivalent to this, so long as what? If what?
3 times
The absolute value of negative 5x is less than 1.
So even if it's a constant being pulled in, it's
Yep.
only the u.
Yeah, it's the u, okay? This is the part that dictates, that's the thing that needs to be less than 1. The absolute value that needs to be less than 1.